11i, area between two curves. Today we're learning about finding the area that's between two curves. What you need to be able to do is recognize which curve is on top, or the higher one, the one with the larger y value. You need to be able to integrate the two curves and then subtracting the area of the lower curve, which are the smaller y values, and then identify where the areas must be split due to signed areas. So in a nutshell, what or how could we find the area between two curves? So over here I've got my first curve, which is my line, and then I've got this curve here. So if I wanted to find that green area, what can I do? Well, if I find the area that is underneath this line here, which is the one that's on top, it's the higher one, and I also find the area that is lower, this lower curve, so that's the yellow area there, what I could do with these two areas, the green and the yellow, is simply subtract them. So if I take away that area, that yellow area, I am left with the green part. And that is exactly what this exercise is all about. So to find the area between two curves, what we need to do is we need to integrate between 2 points A and B, which are the points of intersection. So if I go back, you can see that these are the 2 points of intersection. So that's my first x value and my second x value. So that would become your A and B of my top curve or the upper curve minus the lower curve. So that is how you find the area between curves, and as long as you follow this rule, you should be all good. So let's go for this example here. Find the area that is bound between the curves y equals negative 2x and y equals x squared minus 3. Of course, we must always sketch the graphs to be able to see which curve is upper and which curve is lower, and also we need to be able to find the points of intersection because that creates my boundaries. So let's go ahead and start sketching the curve. We're going to have our first curve, which is y equals negative 2x. So that's going to go through the axes. That was not a very good job of going through the axes. There we go. So that's y equals negative 2x. And then, of course, we have the parabola x squared minus 3. So that should look something like this. I'll sketch it in a different color just so we can see it. Center it a little bit. All right, so I've got my black curve, which is y equals negative 2x, and I've got my red curve, which is y equals x squared minus 3, and then I'm just going to shade in the area that we need to find, which is this over here. So hopefully from the diagram below or before, you can sort of recognize if I were to find the area underneath the line and subtract the area underneath the parabola, I should be able to get that area in between. Now, it might seem confusing because there is negative area, and a lot of students are always tempted or get confused, like, there's negative area, do I have to take it away, just like we've been doing? What I want you to do is treat this as a separate rule, because it does end up cancelling out. And I'm very happy to sit down with you and show you. You might want to try it as your own experiment as to how that works with negative area, but don't worry about negative area with this. It's just always the top area or the top curve minus the bottom curve, and it will always give you that area inside, despite the fact that there is area underneath the x-axis. It will always work out as a positive area. So let's go ahead and do this. The first thing that I need to do is find my intersection points over here, because that's going to form my boundaries. So to find those intersection points, I'm going to make the two curves equal to each other. I'll take everything over to one side. It forms a beautiful quadratic because that's just x. Let's go x plus 3 and x minus 1. So we get x equals negative 3 and x equals 1. So that's my 2 points of intersection. I don't need the y values. It's irrelevant. I just need the x values. All right, and then all I have to do now is integrate between these two curves. So negative 3 to 1. The top curve, it's very important which one you recognize which one's the top curve. So that's negative 2x. And what we're going to do is we're going to subtract the bottom curve, which in this case is the red curve, x squared. And you need to make sure you put in brackets, or if you don't put in brackets, that's fine, but you have to remember to expand the negative to every term. Okay, so from here, it should all just be familiar stuff. So now that's 2x, x squared minus 3 dx. I know how to integrate this, so that'll end up being negative x squared minus x cubed on 3 minus 3x, and that will be between negative 3 and 1. All right, matter of substitution now. So that'll be negative 1 squared minus 1 cubed on 3 minus 3 times 1. minus, again, you need to subtract everything. So I'm just going to chuck the bracket in. Negative 3 squared minus, there's so many negatives right now, minus 3 times negative 3. All right. So negative 1 squared is just negative 1. This will be negative 1/3 minus 3. Lots of expansions here. So negative 3 squared is 9, just positive 9, and then minus minus will make it also positive 9. Here, negative 3 cubed is negative 27. With another negative makes it positive 27, but with another negative, it makes it negative 27 again. However, we have negative 27 on 3. So that's just going to be negative 9. And then here we've got negative 3 times negative 3, which will be positive 9. All right, let's add that all up. So I'll end up with negative 1 minus 3 is negative 4. The 9 and 9 is 18. Minus 9 is going to give you 11. Minus, we've got the 1/3. And when we subtract that away, we get 32 on 3 units cubed. All right, next question. So similar idea, find the area bounded between these two curves between x and 1. So this time they've given us specific boundaries. It's not about intersection points. They've actually told us where to draw our lines, and we need to find that area. So as always, we must sketch. In this case, we've got a hyperbola and we've got a line of x. So here's y equals x. I wish it would go through the axes, through the origin. There we go. And this time I'll draw my other curve in green. It's just a hyperbola, so it looks something like that. All right, now we want it between x is 1 and x is 3. So if I were to label that on my graph, here is 1 and here is 3. The way to check that, actually, the way to know where 1 and 3 is, because it's true, I didn't just magically pull those numbers out. We should actually find that intersection point, because how do we know? Maybe 1 and 3 happens to be on the other side. So probably shouldn't have done that. Let's find the intersection point and then let's figure out where 1 and 3 is, because yeah, you generally wouldn't know. So to find the intersection point, we're going to make the two equations equal to each other. I'm going to multiply over by x, so I get x squared, and then I'm going to take the square root of both sides. I don't know why I drew that. That's just plus minus 2. So in fact, these two equations intersect at plus and minus 2. So that's how I knew that 1 is on this side and 3 is on this side. But you should definitely find the intersection points properly, like I just did in that second one, not just assume. All right, so now that we know where 1 and 3 are, I can shade in the region that I need to find. So that's this part here and this part here. Now this one's a little bit interesting. It's not as clear cut as the one before. So previously we just had line minus parabola, very obvious. But here we've got something different going on. You can see that before 2, I've actually got this green curve minus the line. But if we were to follow our rule, which is upper curve minus lower curve, what we can see here is that the upper curve is actually the line and the lower curve is the parabola. So previously when we integrated and it was just one curve, we always had to create different integrals when it was above the axis and below the axis. When we've got two curves, your different integrals occur when your curves change. So this time I've got the green curve minus the line, and then here I've got the line minus the curve. And it's very important that the order is correct. Otherwise, your negatives and positives won't work out correctly. So another reason why we need to know this intersection point is it does form our boundary. So for my first integral, I'm going to integrate between 1 and 2 of the green line. Let me just highlight what is what. So this is the green curve, and this one is the black curve. I can't really highlight in black. I'll just circle in black. So 1 to 2 of, and we've got the green curve minus the black curve, which is x dx, and then we're going to add on the area, and it's this time it's between 2 and 3 of the black curve, so that's the line, minus the green curve dx. So it's really important that you separate it, and just a general rule, how do you separate it? It's just where the curves intersect, and the lines are going to change. All right, from there, everything is normal. So now we just integrate as normal, we substitute, and so on. So let's go ahead and do that together. Remember, 4 on x turns into a log. So that's going to be 4 log ex minus, and that'll be x squared on 2, between 1 and 2, plus, and this time what's going to happen, it'll be x squared on 2 minus 4 log ex, between 2 and 3. All right, substituting stuff in, so that'll be 4 log e2 minus, I'll just do this in my head, 2 squared is 4, divided by 2 is 2. When I substitute the 1 in, that just, well, that's going to become a 0, but I'll write it out anyway. Minus minus becomes a plus, and then that becomes a half there. So that's for our first one. Now let's move on to our second one. We might need a little bit of space, so I'll just draw a little bit of like that. All right, next one. So subbing right in, 3 squared is 9 on 2, minus 4 log e3, and then minus 2 squared is 4, 4 divided by 2 is 2, and then 4 log e2. I actually made a mistake there. See how I just wrote that negative? It becomes a positive, because really what should have happened is you should write it in brackets and then expand, or if you want to do the shortcut, that's fine, but you must remember to do that. Okay, we now have all of these values that we need to work with, so now it's just a matter of adding, subtracting, and putting stuff together. What can we see? Well, this is just going to be 0, so that's really nice. Is there anything else that cancels out? No. Negative 2 and negative 2 becomes 4. I might just start writing things out. So that becomes negative 4. We've also got 9 on 2 plus a half, so that's just going to be 10 on 2, which is 5, so plus 5. So that's taken care of. And we have 4 log e2 plus 4 log e2. Remember, when you add 2 logs with the same front, you multiply what's on the inside. And I mean, this is exactly the same. So we could probably deal with this first. 4 log e2 plus 4 log e2 means we need to multiply the inside. So that's going to be 4 log e4. And then when I'm subtracting a log, I need to divide by it. So that'll be 4 on 3. So hopefully that made sense there. So when you multiply the 2 logs, you multiply the insides, and then, sorry, when you add 2 logs, you multiply the insides, and when you subtract the log, you divide by the inside. So that was 2 times 2 divided by 3. So that's how we ended up with 4 on 3. All right, and then negative 4 plus 5 is going to be 1, plus 4 log e 4/5. And because it's area, we'll write units squared. Okay, so just to paint this as a general rule about our curves switching upper and lower, this is what it looks like in this diagram, and this is how we would complete it. So we have to swap integrals, or create a new integral rather, every time the curve changes, and that's always the boundary would be whatever x value that happens at, so the intersection point. So to practice that a couple more times, we'll do example 31 here. Find the area of the region enclosed by this graph. F of x equals x cubed, and g of x is equal to x. So again, let's go ahead and sketch our 2 curves. Might be a little bit more colorful this time, and use 2 colors. Oops, that was silly. Doesn't just automatically, it's going to be a shaky curve. It's just the way it is. And then for x, I'll do that in red. I'm going to try my green curve again. I just like pretty graphs. It's up to you. You don't have to draw a pretty graph if you don't want to, but I would like to. Not the best, but slightly better. All right, let's go ahead and shade in the region that I want, which is here. And here. Okay. Hopefully you're used to it by now. You can see that there are going to be 2 very clear integrals. The first one where the green curve is on top, and the second one where the red curve is on top. We need these points of intersection, of course, to be able to form our boundaries. Now that's just 0, that's fine. But to be able to find that intersection point, I'm going to go x cubed equals x. Remember, don't just divide by x because you'll lose a solution. So you need to take it over to the other side. X squared minus 1, x equals 0, x squared equals 1. So x will equal plus minus 1. So those are our three intersection points. We have -1 and +1. There we go. Okay, and then we just need to build our integral. So what I'm going to have is between -1 and 0, we've got the green curve, which is x cubed, minus the red curve, dx, and then plus, and now it's between 0 and 1, we've got the red curve, minus the green curve, dx. Oops. All right, everything from there is as normal. So I think the only annoying thing about this is we're going to be dealing with some fractions. All right, and substituting. This will actually be quite nice because zeros and ones go into fractions quite nicely. 0 divided by 4 is just 0, minus 0 divided by 2 is just 0. And then minus, so -1 to the power of 4 is +1 on 4. Sorry, that is +1 on 4, but because we're subtracting the whole thing, that'll be -1/4. And then -1 squared is +1, times the negative will be -1, but then times the negative on the outside will make it a +1. Plus, and then over here, we'll end up with a half minus a quarter. And then when you substitute in your zeros, you'll get the same. Now you might not notice something at this point. What I've taken out of this first integral, oops, let me separate them, and what I've taken out of this second integral are exactly the same thing. It's a half minus a quarter. And you might also notice that that's actually the exact same area over here. So in fact, you didn't necessarily need to do two separate integrals in this specific case, only because it's symmetrical. What you could have done is one of these integrals and then multiplied it by 2. It is the exact same thing. It is definitely faster, less of a mental load, but it's also about being able to recognize that. So I've done it the long way just so you can recognize that it's the same, and then it's up to you whether you want to do them as two separate integrals or one integral and multiply by 2. Either way works. Okay, so we simply have a half plus a half, which is 1, and then minus a half. So overall, I'll end up with a half units squared. All right, final example for today. Find the area of the region enclosed by the graphs of f of x equals sine x and g of x is equal to cos x, and they've given us two specific boundaries again. So that's pi and 4 to 5 pi and 4. So let's go ahead and sketch this. I'll draw my sine curve firstly. Oh, so when I hold it, it turns it into a shape, but it doesn't recognize the sine curve as a shape. It's a strange line there. Okay. And then the cos curve I'll draw in purple. All right, it's more or less accurate, hopefully. So that's 2 pi, that's pi, pi on 2, and 3 pi on 2. Sorry, pi on 2 should be at the cos intersection. Okay, now in this case, what they want us to do is between pi and 4 and 3 pi and 4. So we just need, and 5 pi and 4, sorry. So we need to find those values as to where they occur. Now, a lot of the time, what it'll actually be is, because especially it says find the area of the region enclosed by this graphs, they're most likely just telling us that they are the two intersection points. So that's the parts that are enclosed by the two graphs. So even though they've given me the values of x, because it's the area enclosed, it will be this section here. But what we can do is we can just check that that is definitely the two intersection points, and that those are the x values that they've indicated. So just as a little bit of a check, let's make them equal to each other to find those intersection points. and see what happens from there. So when I have sine equals cos, what we do is we divide both sides by cos to turn it into tan. And then where does tan x equals 1? So positive 1, think of tan being positive in the first and the third quadrant. So that'll be pi and 4 and 5 pi and 4, which are the values that they've given me. So that's what these intersection points are here. So that's pi and 4 and 5 pi and 4. So these two values is the area that is enclosed between the two curves. Okay, that makes our life really easy because we don't need to do more than one integral. It's just one integral here. We can see that it is the sine curve minus the cos curve. So the black curve on top and the purple curve on the bottom. All right, let's go ahead and integrate all of this. Move this to the side, make it nice and small. All right, so we'll have between pi and 4 and 5 pi and 4 of sine x minus cos x dx. And now integrate. Sine x goes to negative cos x. Cos x goes to positive sine x, but there's already a negative there. And now we can substitute all of our values in. So I have negative cos 5 pi on 4 minus sine 5 pi on 4. Now this is going to get confusing because remember there's a negative on the outside of all of this, and then consider these are both negative, so the negative and negative, everything is going to be a positive. So it'll be plus cos pi on 4 plus sine pi on 4. All right. So everything's pi and 4. So when we're working with sine and cos and pi and 4, it's always 1 on root 2. It's really just about what quadrant is it in. So 5 pi and 4 is in the third quadrant. Cos is negative there. Times the negative, that's going to be a positive 1 on root 2. Same thing with sine. And then in the first quadrant, they're always positive. So it's just 4 lots of that, 4 lots of 1 on root 2. We can rationalize the denominator if we'd like. So that'll be 4 root 2 on 2, which simplifies down to 2 root 2 units squared. Okay, that's the end of this exercise. So hopefully you can see that really the hardest part about all of this is being able to build our graph and knowing what to subtract. Once we've done that, all of this is very routine. So just remember, it's always the top curve minus the bottom curve, and you won't go wrong in this exercise. Please go ahead and do the questions in your textbook.